Okay, the first part on estimation, we're going to be looking at least squares estimation as a mathematical solution. That is, as a mathematical algorithm that we're going to apply to the data to derive estimates. Now remember from lecture 2, we said that an estimator is a function of data x, and that's precisely what we're going to demonstrate here with the squares. It's sometimes called ordinary least squares, and occasionally we use the acronym OLS, ordinary least squares. So I'm just going to outline in this part of the lecture how it works mathematically. Okay, so the observed data that we have available for estimation of the parameters of the linear model take the form of n, I equals 1 to n, so indexing by I, observational pairs. So we've got data on x1, y1, x2, y2, up to xn, yn. Notice that because it's data, we're using lowercase letters because these are observed values of the random variables x and y. So some definitions that we're going to cover here. Fitted or expected values. So for our regression function, we're going to refer to the part of the function a plus beta x as the fitted or expected value of y, conditional on x. The notation we use for fitted values is this hat above it's the same as we use for an estimate actually, hat. But in this case, we're not going to put hats above alpha and beta because this fitted value will depend on the values of alpha and beta that we're going to choose, and that's what we're going to use our algorithm to do. So we're going to derive a fitted value by choosing parameters alpha and beta. But the fitted value is this part of the model. The residual, and this time is EI, not curly EI, for each observation, is the difference between the actual value of I and the fitted value given by the regression line for whatever values of alpha and beta we choose to use. Now we've written this as EI, not curly E, because it's not the actual population error of the regression model, it's just the difference in the observed data between yi and the fitted part of the model. Okay, so it's not the population error, it's the residual. We call it the residual. And then we're going to define a quantity known as the residual sum of the squares. We denote it by S subscript E squared. It's the sum of the squares of the residuals, that is, the sum of the squared values of the observation on y minus the fitted value, which is equal to the sum of yi minus alpha minus beta times xi squared. And that is the quantity that we're going to try and minimize. So this just demonstrates what we mean by fitted values and the regression line. The fitted value is given by the line a plus beta x. It's that straight line there for a data set that we've drawn a line through. So each point here on the scatter represents a value of y corresponding to a value of x. Okay, for each, that's each of our y, I, xi pairs. We've drawn a line through the data, and the difference between the regression line and the actual value of I is the residual, and it's shown by the red lines there. Now, we could have drawn different lines at different slopes through this data, and that would correspond to different values of alpha and beta, and that would give different errors if we shift the line in certain directions. So what we're going to do in ordinary least squares is we're going to try and choose the values of alpha and beta, and therefore this line, by minimizing the sum of the squares of these residuals. That's the principle. Okay, so for fixed data, x and y, the value of the residuals and the residual sum of squares depends on the values of alpha and beta that we choose. I've just said that. And the technique we're going to use to estimate alpha and beta to choose those values is least squares estimation, which is going to aim to make the residuals, or more correctly, the residual sum of the squares, this quantity here, as small as possible. So least squares estimation, choose values of alpha and beta to minimize the residual sum of the squares. And it's actually just as simple as that. We're just going to minimize this expression. So therefore, the least squares algorithm, there's nothing complicated here. It's simply an unconstrained quadratic optimization problem. And all we need to do is partially differentiate this equation with respect to alpha and partially differentiate with respect to beta, set them equal to 0, and that is going to give us the first order conditions for a minimum. And that's them derived there. So this is the first order condition for a minimum with respect to alpha, and this is the first order condition for a minimum with respect to beta. Now, rearranging those first order conditions gives us what's known as the normal equations of the least squares estimator. They're written in this form here. So from the first normal equation, this is the one concerned with alpha, we can solve for an estimate of alpha using these expressions. We then substitute alpha into this, so we solve for alpha using this equation and these expressions here, and that would help you do it when you look at this in your own time. We then substitute our estimate of alpha into the second equation to give us our expression for beta. And of course, because it's an optimization problem, we want to make sure it's a minimum, so we have to check the second order conditions, and we do this by studying the Hessian matrix of second order partial derivatives, which in this case is positive definite, and therefore we know that our stationary point is a minimum. So using what we've just explained, this process, we take the normal equations, solve for alpha, plug alpha into the normal equation for beta. That gives us our least squares estimates of alpha and beta. We write them, of course, with a hat because they're estimates. The least squared estimate of alpha is mean of y minus beta hat mean of x. That's our estimate of the intercept. Our estimate of the slope parameter can be written in this form here. It's the ratio of the sum of the cross products, this expression here, to the sum of squares, which actually can be written as the covariance of x and y over the variance of x. And a full derivation of the least squares estimates is given in the review slide. So in your own time, please follow this calculus and algebra through, and that will explain precisely how we get to each estimate, the estimate of alpha here and the estimate of beta here. We don't need to do it now, you can do that in your own time. So let's make some observations then on the least squares estimates. The estimate of alpha we obtain, given by this expression here, shows that the least squares regression line always passes through the point x bar y bar, which is the mean of the data. With no intercept in the model, the regression line will pass through the origin. And we'll look later at an example where we're going to estimate in practice the intercept, and we'll make some comments on this particular theme. But the estimate of the intercept is essentially the expected value of y when x equals 0. So it's this expression here. But that may or may not be an interesting quantity. Quite often the intercept can be difficult to interpret, particularly in a multivariate setting where you have k independent variables. The estimate of beta we've obtained is the ratio of the covariance of x and y to the variance of x. Now, covariance, as you know from last week, measures the strength of a relationship between x and y. So when covariance is positive, that's telling us that large values of x are observed with large values of y. When the covariance is positive, it means also that small values of x are observed with small values of y. And when the covariance is negative, that means large values of x are observed with small values of y. So this is telling us essentially the slope of the regression line. Is it sloping downwards or is it sloping upwards? Yeah. And we interpret beta as the change in the average value of y for a change in x. So it is this relationship here. That's what beta, the solution we get from these squares. But what it's telling us is, how does the average value of y change as x changes? If it's negative, it means that as x is increasing, y is falling. If it's positive, it means that as x is increasing, y is also increasing. So I hope that's fairly straightforward on the algorithm. It really is that simple. All we've done is set up a function that we want to minimize, in this case the sum of the squares of the errors. That is a simple unconstrained optimization problem. We use partial differentiation to find the optimum points. We check the optimum points and indeed a minimum by looking at the second order conditions, and then we just use a little bit of algebra to go from our first order conditions to solving for alpha and solving for beta, and that is the mathematical algorithm that we use. It's called least squares estimation.